wrap up biasing with a bit of a summary here. So there were three biasing circuits. There was the base bias, the emitter stabilized bias, and the voltage divider bias. These circuits are really the same circuit. Once we take the base resistors and we Thevenize them into a base drive, you have the same circuit, and you would solve them the same way. You'd solve for IB using the same equation. And that would be this equation here. Basically, VCC minus 0.7 over RB plus beta plus 1 times RE. All three of these use the same equation. Now you might say that on this one over here, that I'm not right, because over here, this one is a little different. There is no RE on the bottom. Well, what's happening in this one here is there is an RE on the bottom. It's just 0 ohms because it's a short in the circuit. So that cancels this thing on the bottom, leaving you with just this. And the other thing that you might notice is you'd say, but these two have RB and this one has RTH. Well, in fact, these ones are actually using RTH as well. But in these two here, RTH is just a single resistor, and it's this one, the base resistor. So it's all the same. Three big takeaways from biasing. All the equations are the same. It's just I equals a voltage over a resistance. And the voltage basically is the voltage around the loop. So the loop voltage divided by the loop resistance. The loop voltage is going to be that minus 0.7. And the resistance is going to be the sum of the resistances in the loop. In this case, it's RB. In this case, it's RB plus RE. However, what we usually want to do is move these resistors to the same side. So I like to multiply this by beta plus 1 and move RE over there, which leaves us with this equation. So I usually take the resistances to the base side. However, you can find IE just as easily as IB if you take the resistances over to the emitter side. So if I take this guy over to here and divide it by beta, then if I took the loop voltage over that resistance, I would get the emitter current. And that formula is down here. So IE is a voltage over a current, and it's the loop voltage over the loop resistance, but we move RB to the emitter side to get the emitter current. So if you get all the resistance over on the emitter side, you get emitter current. If you get all the resistance on the base side, you're solving for base current. Number 3, voltage divider bias is better because it's got 2 resistors instead of 1. So that makes it twice as good, right? The answer to that is no. The only real advantage to voltage divider bias, the only reason it's better, is that when I use a voltage divider like here, I can use lower resistor values, which results in a lower base drive resistance. So in this one here, the resistance in this one was about 680K for both of these, rather high resistances. While when we did the voltage divider bias, the resistances in this circuit were more down around 20K. So it's a much lower resistance. And effectively, this resistance is the source resistance of the base drive circuit. So if we have a lower resistance, we have a stiffer source to drive the base. For example, if I have 100K here, which one of these is going to resist drops better or hold this voltage up when that switch is closed than the other? Well, if it's 200K, when you close this switch, it's going to drop to 1/3 its original value. If it's 20K, it's going to drop to 5/6 of its original value. So the lower the source resistance, the stiffer the source, and less impact the beta of the transistor has, because there's less impact of what this does when you hook it up. Biasing summary number 2. Approximations. You have to be a little careful with the textbook because he uses a lot of approximations. The guy that wrote this textbook, he's been working on this thing for like 30 years. I think I used it in college. So he often uses approximations without any explanation as to where they came from. He just kind of starts throwing them out and using them. Good example of that is section 7.5 and 7.6, where there's voltage divider bias and exact voltage divider bias. What's the difference between those two? Well, in an exact voltage divider bias, and this is the one that I usually like to use, and I'll explain why in a minute. What we do in an exact VDB is we take these two resistors and we Thevenize them, and we find the Thevenin voltage here, and we turn that into a base drive circuit. And then we solve for IB or IE using the standard formula. However, in section 7.5, he starts off that section talking about approximate VDB. And what he does is he does the voltage divider here to find out what the voltage of this point here on the base is. And then he goes over here and he just connects that straight to the base of the transistor. So he has dropped RTH entirely. This is an approximation. Because he picked the values, he knows that he can do that without checking. And what happens from there? Let's say the Thevenin voltage was 3 volts, and here's a 0.7 volt drop. If this is 3, then the voltage at the emitter is going to be about 2.3 volts. And we had a 2.3 k ohm resistor on there. We could very quickly determine what IE is. So VRE is just going to be the Thevenin voltage minus 0.7. And then the emitter current is going to be that voltage divided by the emitter resistance. So it seems like this could save you a bunch of work because I don't have to calculate RTH or IB or IC, and it works as long as IE ends up in the middle of the load line. Seems like I can get started pretty quickly with this method. However, there's a bit of a problem with this method. A little later on in the text, he tells you that there is a test. And everyone hates tests. It's on page 256. Essentially what the test does, the reason there's a test is that the approximate method only works if the voltage source that's driving the base is a stiff source. And in that case, so it only works when RTH is much, much less than beta times RE. So if you want to use the approximate method, what he tells you is the first thing you have to do, you have to do solution 1. You have to run the test, and if the test passes, so you have to calculate what RTH is and compare it to 100 times beta R prime E. And if the test passes, then you can use the approximate VDB. And if it fails, you must use the exact VDB. The other solution method is always use exact VDB. So let me demonstrate this to you in a little diagram. So what Malvino is saying is that first thing you should do is you should run the test. And the test is determine whether or not you can do the approximate method. And if you pass the test, you can use the approximate method, which is slightly reduced in work, but not really, because the first thing you had to do is you had to run the test. And if you fail the test, then you can do the exact method, and that'll work. Now, my opinion on this is 3 things that I got to remember, some of which I may not remember correctly. So what I generally tend to do is I go, you know what, this is going to be my method. I'm just going to do the exact method. Basically, I like to have one hammer for all the nails, and it works all the time. So with that, I'd say let's go do some biasing.